In our first example, we have three forces, each of known magnitude and direction, applied to the I-beam through three cable segments. We are asked to determine the resultant force applied to the I-beam. The cable segments themselves, and even the I-beam, are irrelevant to the determination of the resultant force, so we can declutter our figure and replace it with this. As an aside, you should note that lines of action of the three forces intersect at the origin. Such force systems are said to be concurrent, a term we'll see again in Chapter 4. For now, though, the task at hand is to add these three forces together to get a resultant. We noted earlier that vectors obey a commutative law of addition, and so the order in which we add them together is arbitrary. We could begin by simply adding them in the order that they appear. We could add F2 to F1 and then F3 to F2 to get the resultant. But there are many permutations of this that are acceptable. We could start with F3, add F1 to F3, and then add F2 to that to get the resultant force. I will choose the ordering on the left and add vectors together sequentially so that I can use what we know about triangles, the law of sines and cosines, to get the results. In particular, I will first add F1 to F2 to get an intermediate resultant, which I'll call Q. Then add Q to F3 to get the final resultant, R. Focusing first on the triangle whose sides are defined by the lengths of F1, F2, and Q, we can make note of the angles that we know from the problem statement and realize that we know one of the angles in this triangle right away. We're given in the problem statement that F2 makes an angle of 60 degrees from the vertical. That in turn means that F2 makes an angle of 30 degrees with the horizontal. It's also the case that F1 makes a 45-degree angle with the horizontal, and so the corresponding angle between F1 and the horizontal here is also 45 degrees. This tells us that the angle between F1 and F2 is 75 degrees, so I'll replace what I have here with that angle. We know that F1 is equal to 600 newtons, and we know that F2 is equal to 800 newtons. We have a situation where we have a triangle with two sides whose lengths are known, and we know the angle between those two sides, and that means we can use the law of cosines to get the magnitude of Q. So that would look like the following. We would say Q squared is equal to F1 squared plus F2 squared minus 2F1 F2 cosine of the angle between them, which is 75 degrees. And if we plug numbers in, we get 7.52 times 10 to the fifth, and this is going to have units of newtons squared. The corresponding value of Q then, if we just take the square root, is equal to 867 newtons. Now we have a situation where we know the magnitudes of all three sides of the triangle, and we know one of the angles, so we can find the remaining angles using the law of sines. I'm going to focus my attention down here. We're going to call this angle theta. And what we can say using the law of sines is that sine of theta over 800 newtons is equal to the sine of 75 over the magnitude of Q, which we now know is 867 newtons. So we'll go ahead and write that. Sine of theta over 800 newtons is equal to sine of 75 degrees over 867 newtons, and we can rearrange that to solve for sine of theta. It turns out to be equal to 0.891, and so theta is the arc sine of the right-hand side. That turns out to be 63 degrees. Having now established that theta equals 63 degrees, we can turn our attention to the second triangle and the addition of force F3 to the intermediate resultant Q. Now, since theta is 63 degrees, I'm going to replace the 45 and the theta here with their sum. So I'm going to note that this angle right here is 108 degrees. Since that angle is 108 degrees, we also know that this angle is 108. And from the problem statement, we knew that F3 makes an angle of 75 degrees with the negative vertical axis here. So that means that this angle between F3 and the horizontal is 15 degrees. So I can now say that the angle between Q and F3 is 108 degrees minus 15 degrees, or 93 degrees. So I'll clean this up a little bit and replace the angle between F3 and Q with 93 degrees. Again, we have a situation where we have a triangle that has two sides of known length. Now Q is 867 newtons and F3 is 450 newtons. And we know the angle between those sides is 93 degrees, so we can once again use the law of cosines, first to determine the magnitude of R, then we'll be able to use the law of sines to determine a relevant angle and find the final orientation of R. R squared equals Q squared plus F3 squared minus 2Q F3 cosine of 93 degrees. And if we plug numbers in there, we obtain 9.95 times 10 to the 5th newtons squared. So taking the square root, we get R is equal to 998 newtons. Let's go back up to our figure for just a moment, and now I will define an angle phi between R and Q, and I can again use the law of sines to get that angle. So we'll say the sine of phi over F3, which is 450 newtons, is equal to the sine of 93 degrees over 998 newtons. Once again, I can solve for the sine of phi, and that turns out to be equal to 0.45. And taking the arc sine gives me that phi is equal to 27 degrees. So now I have a final vector description of the resultant R as a magnitude of 998 newtons at an angle that's defined as 108 plus phi, which is 135 degrees from the positive horizontal axis, and we'll represent it like this.